Good afternoon, everyone. So we've been talking about backpropagation, and we'll finish that today. And then we'll talk a lot about PyTorch and how we implement all this stuff in Python. So just to remind us where we were organizing our variables using this computation graph, which shows us how the variables depend on each other. And when we start, we know the data. We have some initializations or previous settings for our learnable parameters. And with those, we first have to find all these so-called derived variables. And we do that by going through the forward pass, which is just going through the equations that define those nodes. So we have a linear stage that creates our hidden scores. Then we put them through an activation, a hidden activation. Those activations go through the second output linear stage, and then we're defining the loss directly from those output scores. To compute the gradients, we do a backward pass where we start at the loss and work our way back. And we started, so to talk about that, we first reviewed the chain rule in terms of these computation graphs. So when we have a variable z that depends on y and y that depends on x, if we want to do dz dx, we can do dz dy dy dx by the chain rule. And if we stick in additional nodes, we said you could, if you want to do three-step chain rule, you can, or you can skip over some of these nodes if you have the expression, let's say, for dz dy. And then we said that in the case that a node has multiple variables at it, that often signifies the fact that there's multiple ways for the information to flow between this node and this node. And so in that case, when there are these multiple paths, we want to use the multi-variable chain rule, which is just a sum over the individual chain rules for the different paths. Okay, so we started working on backpropagation in the simplest case where we have scalar variables and a batch size of 1. So all these quantities here are then scalars. Here we have the equations for our forward pass. And then so for the backward pass, we first worked our way down the top row. We said, what is dj, dz out? And then once we computed that, if we want to do dj, da hidden, we do dj, dz out times dz out, da hidden. That's this equation. And we know this value, we already computed it, so that's just a number we plug in. The only work we have to do now is this additional step, dz out, da hidden. And for that, we just look at the corresponding equation here. We see that dz out, da hidden is just w out. We know that value, and so we can multiply these to compute this partial derivative. And then finally, to do dj dzh, we can do dj dah times dah dzh. And for dj dah, that's something we already computed. And then for dah dzh, we have this equation, and so on. So the key point is that as we move our way through using backpropagation, we keep reusing the things we computed in previous stages. And so at each stage, we just have usually one derivative to compute. And so this allows us to proceed backward through what could be a complicated structure using an organized set of computations. It could be very deep, and it could be that if you didn't know how to do this, it would be very intimidating. But once you see this, it's almost like an algorithm. You can just proceed back step by step to compute all of the gradients. Okay, any questions about this simple case? All right, so then we moved on to more complicated case where we had scalar variables but a batch size greater than 1. So that means that all of these quantities here are a batch of size B. So what we do for the forward pass is the same. It's just that all these I quantities we have to compute for all I. And then when we work on the backward pass, we're doing all our derivations for a specific quantity indexed by I. So we're doing like dj, dzo, I. And when we do this, we have to think carefully about whether we need to use the multivariable chain rule or the single variable chain rule. So for example, when we come to dj, dh, I, if we focus on a particular index I here, we have to ask the question, does that go through multiple variables here or not? And so when we look at this equation, which one do I want? I want this one. We see that if I focus on a particular one of these, one of these for a particular I, it only affects one of these for a particular I. So that means even though there's multiple variables here, essentially they're in parallel, and we're just looking at one of these paths here. So we only have one variable involved at that intermediate node. We use the scalar chain rule. Okay, so that's why there's no summation here. And when we did dj, dzhi, we have to think about it again. We can do dj, dahi, dahi, dzhi, and again, we have to see is there a sum here. But once again, if I focus on a particular zhi, that only affects a single ahi. There's no crosstalk across different i's. And so here we really have, again, the case of parallel paths. And so when we do this chain rule, we use a scalar chain rule. Okay, everybody with me so far? Okay, so let's come to the gradient with respect to the parameters. So the first one we'll do is dj, db output. So here we have to ask, does this single scalar affect all the items in the batch or just one item? And so when we look at this equation, we see that this scalar does affect all the items in the batch. And so we have to acknowledge that there's several here, and so we have to do the multivariate chain rule where we sum over the different I. Okay, but otherwise, it's similar to what we did before. We have, if we just focus on one of the i's, we have dj, dzoi times dzoi, dbo. And we already computed this dj, dzoi here. So for this remaining one, we just look at this equation. dzoi, dbo is 1. And that's how we compute this. So the other cases here, gradient with respect to WO, BH, WH, they're all very similar. And we went through them at the end of the last lecture. Okay. Is this making sense? Okay, any questions so far? All right, so now we're going to make things a little bit more complicated, dealing with vector variables. So here not only, and a batch size greater than 1. So we have multiple items in the batch, and they are vectors. Also vector biases and matrix weights. So the forward pass looks like this. Equations should look familiar. Now let's think about the gradient with respect to these variables. So here, not only are we going to select a particular I in the batch, but we're going to select a particular index into that vector. We're going to call that index k. So we're looking at the kth index of the ith batch element. That's just a scalar zo ik. So the first thing to do is dj, dzo ik. That's going to depend on how the cost is defined. I'll give you some examples in a couple slides. So let's assume we can do that. The next one is dj, dahil. So we're looking at the lth element of that vector AH. So we have to think about, if I look at that one scalar in this vector, does it see multiple paths to the cost or not? So we know when we look at a specific specific batch element, that only affects this ith batch element. So that's not going to cause multiple paths. But what about the fact that this z output is a vector? So this is what we have for the equation that's relevant here. And let's imagine that I look at, let's say this is a vector. Let's say I look at the first element in this vector. So that would be when L equals 1. So how does that affect things? Well, when I multiply this by this matrix, that first element in the vector will multiply the entire first column of this matrix, and therefore that will affect the entire vector ZOI. So all the terms in ZOI will be affected by this this Lth term in AHI. So for that reason, we do have multiple paths here, and we have to use the multivariate chain rule. And this time we're going to sum over the different elements within this z vector, which we're indexing by k. Okay. But now when we do that, everything is reduced to scalars. So we're looking at just the kth element of this ith z vector. So that's zo ik. And so we need to do things like dj dzo ik. We already computed that. And then we have dzo ik divided by d ahil. Okay, so again, that is this equation. So we're looking at one particular index into this vector, and we're looking at one particular index here, and those are connected by one scalar in this matrix. And that scalar is going to be the kth row and lth column of this matrix. Okay, so you can see that when you take the derivative of the kth element of this with respect to the lth element here, there's just one scalar value that connects them, and so that scalar value is the derivative. Okay, does that make sense? Or should I try to explain it again, or does anybody have a particular question? Yeah.
So are we treating the input features as column vectors?
Yeah, so all throughout this course, whenever you see a boldface lowercase letter, it's a column, so that we never have to wonder whether it's a column or row, in which case things can get pretty confusing. So yes, so these are columns, everything is columns. So, and if you look at this equation, this, they need to, this one and this one need to be columns for this equation to make sense. Okay, any other questions? Okay, so that's the main idea. So we'll see it again here. So we have to do now dj dzhil. So we're looking at the ith term in the batch, but then the lth index into that vector. And so we have to ask, we're going to use this AH node as the intermediate one. So we have to ask whether we have multiple variables here. So I'm looking at, again, it's going to be the lth element here. This is the equation here. So if I look at the lth element in here, does that affect many elements in this vector? What do you think? Just one. And why does each element here only affect the corresponding element here?
Because they're both vectors of the same size. You're not.
Yeah, but it's really about this function. Something special about this function.
Because
It's element-wise, or call it separable. Yes, exactly. This activation function works independently on every element of this to produce the corresponding element in this. It's sorry, here it is. This is a illustration. So this is our ZH vector. is our AH vector, and you can see the first element determines the first element here, and so on. There's no crosstalk. Okay, so that's something that's special about these hidden activations. It's not necessarily the case for the output activations. There is potentially crosstalk there, depending on how that's defined. Okay, so coming back to where we were then, we see that, oh, sorry, this one, okay. So for this, if we look at the lth element here, that only affects the lth element here, and moreover, the ith vector here only affects the ith vector here. So here there is just the scalar univariate chain rule when we go through there. So there's, in this equation, there's no summations over k or I. Okay, so that gives us the gradients with respect to these purple nodes. Everybody okay with those? Okay, so then the next one is, what about the parameters? So here, this is again a vector. So let's look at the kth element into that vector. And let's think, how many things here are affected by that. So this is the equation. So first of all, okay, let's talk about I. So if I change one element in this vector, how many of these vectors, how many different i's does that affect? All of them. Okay, so we're definitely going to have a sum over I in the multivariable chain rule. What about over k? So if I change the kth element here, do all the elements here change or just the kth one? So let's say I changed the kth one here, and I'm looking to see what happened here when I changed this one. Like, this is a vector, this is a vector. So the question is, if I change the first one here, does the second one here change? No, right? This is just adding this vector to this vector. So if I change the first element in this vector, only the first element in that one changes. So that means that when I consider this, I don't have to worry about the kth one here affecting different lth terms in this single vector. So I don't have to have a summation over, let's say, L, if L is indexing those. So the only summation I have here would be over I. So it's multivariable chain rule, but you can see I can use single k all the way throughout, and I is just changing the batch index for the different elements in that batch. Okay, so this is how we have dj, db, output k. Okay. Any questions on that one? Is that one making sense, or further explanations needed? Okay, so what about this? This is an entire matrix, so we have to isolate a scalar quantity within there because it's a lot easier to do scalar calculus and vector calculus. So let's look at the kth row and lth column of this matrix, WOKL. And let's ask, okay, first of all, how many, if I change the kth row and lth column of here, how many different batch elements will that affect based on this equation? One or all? All, right? So this guy affects all the different I. Okay, so we're going to have a sum over I. Okay, what about, again, if I'm looking at the kth row, lth column, how many different, which indices into that vector change if I change the kth row and lth column of this matrix? Just one of them. Which will be, what is the index of the one that changes? So I'm changing, again, the kth row and lth column. So which of these will change? So it's going to be the kth. So if you think about, like, if I write an equation for the kth element of this vector, I'm going to take the kth row here times that entire column. So So basically, when I'm looking at the kth row, lth column, that's going to affect the kth output. So here we have K, 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 K. So K here fixes the K at the Z I have to look at, but I have to look at all the different I's across the batch. And when I do this, DZOIK divided by DWOKL, so again, we're looking at, for example, let's say we look at the first element in this vector. If I look at the first element there, I know that is affected only by the first column here times all of these. So, but actually I'm doing the derivative with respect to only the lth column of this. So DZOIK, DWKL is just going to be the lth entry into here, DAHIL. So it's just a matter of sort of imagining. It helps to put maybe indices on these. So K is coming down this way. K is also coming down this way. L is going across that way, and therefore L is going down this way. So now when I'm looking at the kth element here, that affects this row. And if I'm looking at the lth column here, that affects the lth row or lth element of this vector here. So that's why we have this. Okay, so again, linear algebra continues to be important throughout the course. All right, any questions on this equation? Is this still making sense? Okay. All right, so the other ones are really no different. So when we do DJ, DBHL, we're looking at the lth element here. We can use this as an intermediate node, and we would ask the same question, like if I change this lth element here, first of all, do I affect all the items I in the batch? The answer is yes. From here you can see if I change the lth element here, that affects all the items in the batch. Second, if I change the lth element here, which of these elements are affected? You can see that only the lth element here will be affected, so we don't have to have a sum over L here. We can fix L throughout. And this DZHIL, DBHL, that's an easy derivative. That's just 1. And this is something we already computed, so that's how we tackle this. And the last one, we're going to look at the lth row. The lth row, I'll draw it this way. Lth row and the jth column of WH. So again, lth row, jth column, that means we're going to be coming down this way with J. And so when we do DZHIL, so again, we're looking at just the lth element in that vector, which will isolate the lth row in this. And now we're going to do DWHLJ. So the lth row, jth column here, that will only affect the jth entry of xi. So that's where we get that. So, so we made it our way all the way through this backpropagation with vector variables and a batch size greater than 1. Okay, so any questions on any of this? All right, so you will have a homework problem in Unit 8 where you'll get to work out some of these details on your own for a slightly different problem than this. Okay, so we have all the equations stated in terms of summations. As we know, summations are not so useful for implementation because we'd like to implement things with matrix and vector multiplies, matrix multiplies, and so on, because they're a lot faster. And so that's the next step, is to rewrite these in terms of matrices and vectors. So to do that, we need to establish our notation, and we're going to be consistent with how we've done things all the way since Unit 2. So if you remember, when we construct our feature matrix X, we always have the sample index I coming down the row, and we have the feature index J coming across the columns, right? That's how we've always done it. So we're gonna do that. And notice that there's a transpose here. And we're also working with a mini batch, not the entire data set. So when we think about the different samples we're working with, we start with sample index I, end with sample index B. And then each one of these is a d-dimensional column vector, where d would be the number of features in our data set. So in our demo, it was just 2 features. Okay, so this is just consistent with how we've done things all semester. And then all the other quantities here are defined consistent with that. So we always have, okay, so notice because of the transpose, the batch index is going down the rows. So we construct Y the same way. The batch index is going down the rows. And then the hidden Z's, same thing. The batch index is going down the rows, and the dimensions of those hidden score vectors are going across this way. In our demo, we had 4. And we have the output. The output scores are constructed the same way, and even the activations, again, the same way. So all the vectors have the same number of rows, which is B. Okay, so then given that, we just need to rewrite some of these quantities in terms of, I wish I could fit it on a page, let's see. So if you look at the top of the page, you can see the equation for this single i's, and on the bottom page you can see the vector equation. So essentially what we need to do is we just want to, so these are column vectors for the ith sample. We want to translate that into a row vector, right? So that we can stack them top to bottom. So what we're going to do is we're going to transpose this. Imagine on the left you'll have Z transpose, then this will give you X transpose, W transpose, and this will be B transpose. So that would give us 1 row, basically like 1 row like this, and then we're just going to stack that vertically, all the different batch things we're going to stack vertically. So that's how we get this equation here. So again, I is, no, in this case, I is going this way, and I don't know what variable we should use there. So for the hidden nodes, I used L. Okay, there we go. And here I is going across this way. For the W hidden, let's see, I used K this way. And of course that means I'm using K this way. And it means I'm using L this way. Okay. For the let's see. There might be a mistake here. So this is a column vector. So when we transpose it, oh no, actually, what am I doing wrong?
1 second.
I think I'm confusing myself in terms of how I define these. Let's see, so one way to think about it would be like I can move this transpose to the other side. And once we do that, now you can see these are the column vectors. So this is like these are the column vectors that we had over here. So I'm just stacking things across column-wise. So I think the explanation I gave a few minutes ago with the transposes was wrong. Apologize for that. So if you think about the transposes over here, and that's this, then we're just stacking the columns from left to right of this equation here. So if I want to stack that single column from left to right, I'm just going to be copying and pasting it. I can do that by multiplying it by a row vector of ones where there's exactly b ones in that row vector. So that's just going to copy that BH over and over into different columns. Okay, so that's how we get the first equation. The next one is easy because since H works element-wise, we can just apply it to all the terms in this matrix to give us the terms in this matrix. This next equation is constructed the same way as the first. And then the last one, we don't really have a way of getting rid of the sum. Okay, so this is how we get the forward pass. Any questions on the forward pass? Okay, so what about these other things? So this we can think of as the gradient with respect to the ith row and kth element of the Z matrix. So that's what we have here. We have dj dz as a matrix, extracting the ith row and kth column. And then over here, we can think of this as the ith row and lth column here of a matrix. Over here, we have another matrix indexed by I and K across the columns. And then we have another matrix here indexed by K down the rows and L across the columns. That's what this tells us here. So now from that, you can see that this is just a regular matrix multiply. You have a matrix here and a matrix here, and this summation does the multiplication of these columns times those rows. So this is just this matrix times this matrix, and that's what we have over here. So this is one of our matrices. This is the other matrix, is just the W matrix here. So that gives us this next one. And everybody good on these two? Okay. The next one is a little different. So here, notice that you have I and L everywhere. So this is, so if you imagine this is another matrix where this is the ith row and lth column of that matrix, you actually want to do an element-wise multiply between these two matrices. So element-wise multiplies are not things we see too often, but there is a notation. Most common notation is this circle with a dot. So this is element-wise multiply between those two matrices, this one and this one. Okay, so any questions on this one? This is also called the Hadamard product. Okay, then we have gradient with respect to the parameters. So this is just going to be the kth element in dj d vector b0. So here's the entire thing. And so here, again, imagine that this k is going down the rows of that vector. That means that k must go down the rows of that matrix, and I must go across the rows. And I, it has to come down this way. Actually, sorry. Do I have that right?
That's right.
So one thing you notice, though, is that we would like this to be kth row, ith column, but as you can see, this matrix is ith row, kth columns. So we actually need to transpose this matrix to get it to work out with this summation like this. So here we have transpose of that gradient matrix. And yeah, so this is just a vector of ones. So that's this vector of ones, and there's a total of b of them. Okay, so that's this quantity. Any questions on this? Okay. Okay, what about this one? So here we have a matrix, kth row, lth column. Is that, let me check. Yep, that's what we want over here. No transposes there. Okay, but over here, to be consistent with these, we have to have K coming down this matrix, L going across, no, sorry, it's, yes, L going across. Maybe I forgot to notate, there needs to be a transpose here. And for the same reason, we need to have a transpose, oh, I messed up. This should be I. Because we're going to be summing across I. So for that reason, we want a transpose on that matrix, which will swap the K and the I. So then when I comes down this way, this is oriented correctly because we want I to come down the rows and L to go across the columns. So this is fine. This is the matrix AH here. So as we can see, here's the matrix AH, and there's the transpose on the DJ DO matrix. Okay. And the last two are identical in structure to those. Work the same way. Okay, so that's now we have everything written in terms of matrix vector multiplies. We have the forward pass, and then here we have matrix product, Hadamard product, matrix vector multiplies, matrix multiplies. So now everything can be done very efficiently. All right, so that's the hard stuff. That's over now. Any questions on that? All right, so maybe you can spend some of your own time looking at it. But here's just a summary of what we did, the forward and backward passes expressed with the matrices and the vectors. So these are all our parameters. So we went through the forward pass, computed all those quantities. Once those are all computed, we do the backward pass. On the next page, we'll show the expressions for this, for some popular losses. But then otherwise, we have these matrix vector, matrix type products. Here's a Hadamard product, and so on. So this is what we need to do to compute it. Thankfully, we don't have to program this ourselves. This is implemented in packages like PyTorch and TensorFlow, and that's what we'll spend the remainder of the lecture talking about. Okay. Except for one other slide. So I promised you that I would show you some examples of this stuff. And these are actually things we've already seen before, but just to see them again. Imagine that we're working with binary cross-entropy loss. So that means we have one output node. And as we derived back in Unit 5, we have the sum over the batch elements I of this J, which this is our negative log likelihood for the logistic model. And so when I want to do the gradient with respect to ZOI, you can see that's pretty straightforward because in the natural log, you get 1 over this times the gradient of this with respect to ZOI which is just e ZOI. And then you have the derivative of this with respect to ZOI, which is just minus yi. Now, if we were working with K area cross entropy loss, then we need to have K output nodes, or K terms in our output score vector. And we have sum over our batch of this loss, where we derive, also back in Unit 5, this is for MLR, we derive this. So we are using one-hot coding here. So this vector yi is a one-hot vector, so it has, if the ith training label equals k, then for this vector, you have that the kth element is 1 and all the others are 0. And given that one-hot coding of the output labels, this is what we derived for MLR. And so now when we want to do dj, dzo, ik, you can see again, because of the log, you have whatever here is repeated down below, and then you do dzo, ik of this. So there's only one term in the sum that matters. It's the term with the k in it. And then then that gives you this with the k, with the L replaced by a k. And the derivative of that is just that itself. And finally, one more linear term is easy. D of this, dzoik, is just going to be minus yik. Okay, so that fills in the details for what we do here. And that's backpropagation for these two-layer networks. All right, any last questions before we forge on? Okay, so I know that students, they always tell me they find this really complicated, so if you feel lost, don't worry. It's the sort of thing where maybe you have to just look at it on your own time, go through it at a slower speed. Okay, so next thing to talk about is how do we implement all this stuff. Like I said, thankfully we do not have to implement backpropagation ourselves. That's what these packages do for us. And there's a whole bunch of them. These are the most popular 7 of them. Maybe you've heard of a number of these. Probably the most 3 popular out of these would be TensorFlow, PyTorch, and Keras. So that's what we're going to focus on. So TensorFlow was developed first back in 2015. Because it's been around a long time, it's very widespread. It's very mature for deployment. By deployment, I mean like if you actually want to make a practical system, some machine learning thing that you sell that really has to go into commercial use. You know, it's not just developing stuff yourself, then you really need to deploy it, and that TensorFlow has a lot of good tools for that. The original version of TensorFlow was kind of difficult to use. The newer version is better, but in my experience, talking to my graduate students, it's still not great. It's still a little bit cumbersome to use. Keras is something that runs on top of TensorFlow or Theano or CNTK, and basically it's like an interface that makes everything super easy for very common tasks. So with Keras, you can program a neural network in like 2 lines or something. It's very easy, but if you want to do something a little bit non-standard, it becomes difficult because you have to get under the hood, and then you're just better off using one of these tools here. Also, it's a bit difficult to debug because, again, it's hard to see what's happening under the hood because everything's covered up. PyTorch was developed in 2017, so a little bit after TensorFlow. So for a few years, they were playing catch-up, but from the beginning, it was a lot easier to use than TensorFlow. And so now I would say it's just as powerful, maybe not quite caught up for deployment, but in terms of research, academic community, it's now definitely the most popular. So we're going to be using that. There's various articles that have been written about the pros and cons. These are some from a couple years ago. Basically, they say this kind of stuff. In any case, we're going to be using PyTorch. TensorFlow is not really that different, it just differs in the details. So here is the basic recipe, 5-step recipe for implementing this stuff with PyTorch. First, we have to construct the data set and data loader objects. Those are the things that deal with our training data. Second, we construct the architecture of the network. This is where we tell it how many hidden units, how many output units, et cetera, et cetera. Then we have to set up the optimizer, the algorithm, to do our gradient descent, as well as what our loss is. Then we run that algorithm on the data, we fit our network parameters, and finally, when our network is trained, then we can apply it to new test data. There's great tutorials at pytorch.org. You can follow that link if you want to read any of them. But we have a demo. You know, it's the demo for that thing we saw earlier. We have two-dimensional features: the green dots in the middle, the blue dots on the outside. That's the demo we're going to be talking about now. You know, how exactly did we code that? So just to kind of go through the demo then, step one, we have to get our data, training data, into a form that PyTorch likes. So I guess the very first thing we do, we have to import Torch, and then we have to import the data stuff, utilities for data. So the first thing to note is that we have to work with PyTorch's native variable type, which is these torch tensors. So typically we might start with a NumPy array, but we can't use NumPy arrays directly with PyTorch. We have to convert them. So you just do torch.tensor, and now this xtorch, it actually has a bunch of extra stuff under the hood that helps it do the backpropagation. So that's what happens there. And this is basically, these are our training features and our training labels. Okay, so then the next thing is to create what's called a dataset object. So here you can see we're going to give this thing, tensor dataset, our training features and labels. So now PyTorch has them in a form it likes. Next, we're going to create a data loader. And what happens with the data loader is it takes that data set and it adds tools to do random sampling, so to pull out these random mini batches differently every epoch. And it also puts in things like multi-processor support. So if you have several GPUs, the data loader will basically farm out the work to the different GPUs so that they can work in parallel. So that's what the data loader does. It can also, not even different GPUs, it could even be different computers in a network. So it handles all that stuff for you. And just a sneak preview, once this loader is created, when we want to pull out mini batches of data, we have this for loop for batch data in enumerate loader. That so batch is kind of like a counter in this case, and then the data, every time we go through the for loop, the loader outputs this data object, and then you can see here the data contains a pair of X batch and Y batch, so the features and the labels. Okay, so that's the first step. Any questions here? Okay, moving on to constructing the network. So here we're going to import the neural network library from Torch that knows about things like activations and convolutional layers and linear layers like we've been using in this unit. And we have to construct a module. This is like an object for the module. And like the object-oriented stuff we've seen previously, we have a class here with some initialization code that is run when we instantiate this class. And then it has another function here, which is what happens in the forward pass through the network. Okay, so what the initialization code does is it takes in the number of inputs to the network, the number of hidden layers in the network, and the number of outputs to the network. It takes in those variables, and it creates an activation function, which we're going to use a sigmoid for in this case. It's going to create that first linear layer, which is going to have n in inputs and nh, that's number of hidden nodes, that many outputs. We're going to call this dense 1. And then the second layer is going to go from nh to n out. And we're going to call that dense 2. So we basically set up these different blocks. We haven't connected them yet. They get connected in this forward function. So here this just takes in a feature vector x. And as you can see, it puts it through the dense layer. Then it puts that through the activation, overwrites x, takes that overwritten x, puts it through the second linear layer. And in this case, we also have the same activation again. A sigmoid is used twice. And so these outputs are probabilities between 0 and 1. So once we set this up, then we instantiate the model like this, net, and we tell it how many inputs do we actually want, how many hidden nodes, how many outputs. In this case, just a single output. And so now model is our network. That's what we're going to work with. Okay, any questions? Okay, so now we need to tell it how to optimize the parameters. So we have to select an optimizer, an algorithm. So for this, we import the Optim library of PyTorch, and we're going to choose Atom. Atom is the most popular optimizer, but there's many other options. So you could use standard stochastic gradient descent. There's all these different algorithms that have been developed, which are basically versions of stochastic gradient descent with extra things like momentum and all kinds of different things to try to help make convergence faster and jump out of bad local minima and stuff like that. But Atom is usually the go-to thing that people start with. If you want to know more details about all those different algorithms, I've put in some links here that explain them in great depth if you want. So again, we're gonna choose Atom. So we do Optim Atom. We also have to tell Atom what we're going to be optimizing. So model.parameters pulls the parameters out of our model. And then we have to tell it the learning rate. So we're just going to plug in 0.01. If we don't like that, we could try again with a different one. We also have to tell it what is the loss that we're trying to minimize. So we're using this neural network.binary cross entropy loss. I'll talk a little bit about some of the other options, but that would be the binary case. If you have multiple outputs, there's the regular cross entropy loss. Or if you're doing regression, we have things like mean squared error loss, basically is like RSS, or L1 loss. And if you want to, let's say do lasso, something like lasso, you could add MSE loss to L1 loss. Well, you have to be a little careful. You just have to, you have to set them up, but basically you can do things like this. You can just take sums of loss functions. Okay, so now we're basically all set up, and we can finally have our big for loop where we do our training. So we're just going to set up a few things in advance. Number of epochs is going to be 2,000. Print interval just is going to be how often we print stuff out. And we're going to initialize some arrays to store what happens with the loss over the epochs and what is our classification accuracy over the epochs. Okay, so then you can see we have an outer loop, which is over the epochs, and we have an inner loop, which is over all the mini batches within a single epoch. Okay, so the first thing we do in the outer loop is we zero out these counters. There's an error counter and a total counter, and those will just count how many errors and how many samples have we processed as we loop around and around this inner loop. And eventually we're going to use them to compute the accuracy, 1 minus error over total times 100. And yeah. Okay, so then the batch loss is going to basically be just an empty array that's going to grow, that's going to collect the different training losses, the binary cross entropy losses over that epoch. Okay, so then here's the inner loop. So this is where we do the for batch data equals or in enumerate loader, where we pull out random mini batches. So we saw those first couple lines. Now, there's often little things that you have to know about, or you get these errors that are difficult to figure out. So one of the things that we need to do with PyTorch is, it turns out the Y batch we have here is a one-dimensional vector. X batch is going to be a two-dimensional matrix, but it does not like the fact that Y is a one-dimensional vector. So we have to resize it to a matrix with one column. So that's what we do with this dot view. -1 means make the last index of dimension 1. So now X and Y batch are both two-dimensional quantities, and this is what our model wants. So we basically put X batch through our model to get the outputs of our neural network. Then we give that output and the training label to our criterion function, which is that BCE loss, and that will compute our loss. And then we're going to append that to our to our batch loss vector. So we're going to store that loss at the end of the vector, and it will continually grow. Okay, so now we're getting ready to do backpropagation. So the way you have to do this in PyTorch is first you have to zero the gradient, because otherwise it remembers the gradient from the last iteration. So zero out the gradients. And then when you do loss.backward, that's when it goes to the network and does all the backpropagation and stores all the gradients internally. And then we do op.step. It knows where to find those gradients, and it takes a step according to the Atom algorithm. Now your parameters have changed. Now we can also process the output to see what our training accuracy is. So out is what came out of our network. We round it so that it's either 0 or 1, because remember, otherwise it was between 0 and 1. And that we'll call that guess. And then we'll compute our training error. So we look at the difference between guess and Y batch. And if that is non-zero, then we add it to error. And then we just basically keep iterating around and around that inner loop to go through all the batches in one epoch. And then we get back to the outer loop, and we do, in this case, 2,000 epochs. Okay, so in terms of the math, the left column here shows what we're doing. And so when we run this, you can see this is plotting the loss versus the epoch. It immediately shoots down, and then it kind of gradually goes down, and then it settles out. And here we're looking at the training accuracy over the epochs, and you can see it immediately jumps up to about 70%, but then it kind of hovers around there while the network is figuring things out. And then something happens where it jumps maybe out of a bad local minimum into a good one, and all of a sudden the accuracy shoots up to here. So, and that's, every time you run it, it's going to be a little bit different. You can affect the shape of this by changing the learning rate and so on. But that's essentially what happens. The other stuff here is basically how did we compute some of these plots. Maybe what I'll do is we're running out of time. We'll start with this next time, and we don't have much more to do in this unit, but we'll finish this out and we'll talk a little bit about how we do a few of these things next time. So see you guys on Wednesday.